Hello grade 12s, in this video I'm going to be working through example 1 and example 2 from your textbook. These are the examples on the photoelectric effect. Now please remember, although our main focus is the photoelectric effect, you also need to have knowledge of atomic spectra, which follows in your book in the same sort of section as the photoelectric effect. Although it's not a very big section, the section on atomic spectra, it does come up. So in the same way that you would find that the moving stars and planets section in the Doppler effect came up, you will find atomic spectra appearing in your exam. So it's important that you please watch the video that follows. In this example, they say light with a wavelength of 160 nanometers. Nano means times 10 to the power of -9. Is shone onto a metal plate with a work function of this amount. Work function W0. So 160, this here is the wavelength of the actual light, but the work function is specific to the metal. Question number 1 says determine the frequency of the light. So let's remember that in this situation or any situation that you guys deal with, we are dealing with light that is moving at its maximum speed, so that C value. And as a result, we can simply say that C is equal to F multiplied by lambda. In this case, C is 3 times 10 to the power of 8. The frequency is what we're looking for, and lambda is 160 times 10 to the -9. We divide both sides by 160 times 10 to the power of -9, and in the end the answer that we obtain is 1,88 times 10 to the power of 15. Now we need to remember what frequency is measured in. Guys, it's measured in hertz. Frequency measured in hertz. Question number 2. They ask us to calculate the threshold frequency of the metal. Remember, this is the work function of the metal. Now we're looking for its threshold frequency. Remember that work function is simply a form of energy. But you're also given this formula on your formula sheet. So we're simply going to say the work function is equal to Planck's constant multiplied by the cutoff frequency, also known as the threshold frequency. The work function is 8,5 times 10 to the -19 joules. Planck's constant is a constant given in your table of constants. It's 6,63 times 10 to the -34 joules per second. And we're looking for the threshold frequency. Dividing both sides by Planck's constant, we obtain an answer of 1,28 times 10 to the +15 hertz. This is still frequency, so it is still measured in hertz. On to the very last question. They say the kinetic energy of the emitted electrons is what we need to calculate. The kinetic energy of the emitted electrons is specific to this equation on the photoelectric effect, and they are basically asking us to solve for that part. So we're going to say E is equal to W0 plus EK max. This is the maximum amount of energy they may have when a light of a certain frequency shines on them. At the moment, we don't have this energy, this E value. But remember, E is calculated by saying H times Planck's constant. Please remember in your formula that this E value is specific to the light itself, the light that is shining on the electrons. Everything on the right-hand side is specific to the electrons and the metal from which they're being emitted. So we can calculate that E value, and just to complete the formula, we say this is equal to the work function, which we already have, plus EK max. I'm now going to substitute values in. Planck's constant is 6,63 times 10 to the negative 34, and it's available on your formula sheet in your table of constants. The frequency of the light we calculated in question number 1, and it's given as 1,88 times 10 to the positive 15. The work function was given to us over there. It is given as 8,5 times 10 to the negative 19. This is plus EK max. So all that is needed is for us to subtract this value from both sides, and we can then solve, and we say that EK max, the kinetic energy of the emitted electrons, is going to be equal to 3,96 times 10 to the power of negative 19 joules. And that is our final answer to this question. I hope that they're making sense. On to example 2. Here they say the diagram below shows a photoelectric cell. They love to give examples of this kind or give questions involving a photoelectric cell or photocell in exams. So be sure to practice these. They say the photocell consists of a glass tube with a curved cathode and anode inside of a vacuum. They don't always need to mention a vacuum, but a vacuum is a clear indicator of the constant C. They say the cathode is made of a metal with a low threshold frequency and emits photoelectrons with incident light of frequency larger than the threshold frequency. I just need to read that again. The cathode is made of a metal with a low threshold frequency and emits photoelectrons with incident light of a frequency larger than this threshold frequency. Okay, that's fine. The anode attracts the photoelectrons and completes the electric circuit. Okay, an ammeter in the circuit shows the strength of the current. There's the anode. So they're basically giving a big explanation about a photocell and how it works. Now they say if light with a wavelength of 660 nanometers strikes the photocell, the ammeter will show a reading greater than 0. What that basically means is that this here is enough to emit electrons. Now they ask, what will happen to the ammeter reading if the frequency of the light is increased? Remember guys, so I'm going to do this with explanations as well. We say, when the frequency is increased, the energy of the light is increased. Since we are shining light of a higher energy onto this metal and onto the electrons, we find that the electrons will have not only enough energy to be emitted, so not only the work function, but they will also have kinetic energy, and they will therefore be emitted with kinetic energy. If we then go and we increase this value, which increases that value, we're going to increase the kinetic energy of the electrons. Kinetic energy is equal to half mv squared. So that means that our electrons are going to move faster. An ammeter measures current. And since current is equal to change in charge divided by change in time, or even just charge divided by time, if our electrons are moving at a larger speed, it means that the time they take to travel from one point to another decreases. If this value at the bottom decreases, then the current increases. So the correct answer to question 1.1, what will happen to the ammeter reading, is that the reading will become higher. The reading will increase. That is what's going to happen over there. In the next question, question 1.2, they ask what will happen if the intensity, the brightness of the light, is increased. Whenever they speak of intensity being increased, remember, in order for these electrons to be emitted, they need a wavelength of 660 nanometers or lower, because if it's lower, then the frequency is higher. So we first ask ourselves, the light that is shining at the moment, has it got a wavelength or a frequency high enough to emit electrons in the first place? They say yes, it does. So that's fine. Now we say if we increase the brightness, so we're going to increase, I'm going to call it brightness. When we increase the brightness, it does not change the frequency, it does not change the energy, and it therefore does not change the kinetic energy. So none of these things are going to be affected. That is very important. But when we increase the brightness, what happens is more electrons are going to be emitted. Looking at our formula for current, we know that current is equal to change in Q over change in time. We are not changing the speed of the electron, so therefore we are not changing the time in question 1.2. What we are changing, grade 12s, is the charge, the amount of charge that is being emitted. And of course, if I increase the brightness and I have more electrons being emitted, then the change in charge is larger, or the charge is larger, and therefore the current increases. So the correct answer to question 1.2 is that it will increase. There, the ammeter reading will increase as well. On to question number 2. These questions over here on the right hand side, very important. If you don't know them, they're going to cost you about 4 marks. Maybe one in the multiple choice section and one in the section like this, where they actually ask you questions. Question 2 says, tests are conducted with different wavelengths of light. If light with a wavelength greater than 700 nanometers strikes the photocell, the ammeter reading is 0. Determine the work function of the metal. Now, just to start off, what I'd like you guys to remember is that wavelength. So they're speaking about wavelength here. Wavelength is not frequency. Wavelength, we started off with a wavelength of 660 nanometers. Then we went to a wavelength of 700 nanometers. We increased the wavelength. If we increase the wavelength, it means that we went from one frequency to a frequency that is lower. This has a lower frequency than that. Therefore, this has a lower energy than that. I need you guys to understand that. That is why when we went to 700 nanometers, suddenly the ammeter reading decreased to 0. It's because the frequency decreased. That is very, very important. Question 2.1 requires us to determine the work function of the metal. We are looking for W0. That's what we are looking for. So, the fact that they say in this problem that if light with wavelength is greater than 700 nanometers is used, then the ammeter reading will be 0. Now it's a bit confusing, but what they're telling us is that 700 is the largest frequency, the largest wavelength that we can go to. If we go larger than that, it's not going to work anymore. So 700 is therefore lambda 0. It is the cutoff wavelength. And we can use this cutoff wavelength in order to determine the work function. Remember, your work function is equal to HF. Okay, the Planck's constant multiplied by the threshold frequency. At the moment, we do not have the threshold frequency, but we do know that frequency is equal to C divided by lambda. So we can substitute in the place of the frequency C divided by the cutoff wavelength. Alternatively, you could first calculate this F0 and then plug it in. You're welcome to do so. So now we can simply substitute in. We know Planck's constant is given to us as 6,63 times 10 to the negative 34. C is a constant. Remember, we are in a vacuum, guys. So it's a constant 3 times 10 to the power of 8. Lambda 0 at the bottom That over there is given to us as 700 nanometers. So 700 times 10 to the negative 9. And plugging all of this into our calculators, we get an answer of 2,84 times 10 to the negative 19 joules. And that is the work function for this metal. On to the very last problem. We have question 2.2, which says determine the speed. Speed, we're talking about kinetic energy, right? Of the emitted electrons if the incident light has a wavelength of 660. Take the mass of an electron to be this amount. The mass of your electron is also given to you in your table of constants. So please familiarize yourself with your formula sheet. Please, please, please. I don't want you guys to get to your exam and then you don't know where to find values. Go take a look at your formula sheet. Write things down on your formula sheet. Study with your formula sheet. Your formula sheet is basically your summary page. So go print another one out or use the ones I've printed for you, or come and ask me again in class to print out a formula sheet. I don't mind, I will do it. Okay, so over here, since we're dealing with kinetic energy, we know E is equal to the work function, which is constant for this metal. So we found that in the previous problem, plus EK max. The energy can be calculated using that since we have wavelength. So we substitute in Hc over lambda equals this. Okay, and now we just have to substitute the values in. So Planck's constant, guys, is given as 6,63 times 10 to the negative 34. C is given as 3 times 10 to the positive 8. The lambda value that we've been given is 660 times 10 to the negative 9, since it's measured in nanometers. Your work function, we calculated in the previous problem. It is given to us as, we calculated to be, 2,84 times 10 to the negative 19. Where did I get this? We calculated it already. Okay. And sorry, I've run out of space, but this is plus that EK max. So we just need to solve for EK max, and we do that by moving this over. So we take that and subtract it on the other side. In the end, EK max is going to equal to a value of, okay, I don't have this value. No, I do have the value. So it's equal to a value of 1,74 times 10 to the negative 20. But we're not just looking for the kinetic energy. We're looking for the speed. So now you remember that speed is equal to half mv squared. So we're going to say half mv max squared is equal to 1,74 times 10 to the negative 20. By the way, this is measured in joules. Okay. The mass of your electron is given in this question, but also given on your formula sheet in your table of constants. That's V squared equals 1,74 times 10 to the negative 20. So we start off by dividing both sides by this part. When we're done, we take the square root, get rid of the square. And your final answer, your V value, is going to be 1,95 times 10 to the positive 5 meters per second. Okay, to the negative 1. And that is your final answer to this example. I'd like to encourage each of you to work through examples from past papers that involve graphs, because I have not done so in this video. And then if you do have problems with those, you let me know. But just a reminder, when you have graphs, and on your y-axis you have EK, on your x-axis you have the frequency of the light. Your graph is always going to look something like this. The plotted graph will look like that. It's not a direct proportion, not a relationship of direct proportion, because it doesn't cut through your origin. Okay. But remember, your gradient for this graph is going to give you Planck's constant. And if you take the graph and you extrapolate it, which means to extend it, where it cuts through your y-axis, the value you get there is negative the work function. So in other words, the positive of that value is going to give you the work function. Please remember that when you work through problems of this kind, problems involving graphs. Again, I encourage you guys to do so. In the next video, I'm going to be working through the theory on atomic spectra, so I hope to see all of you watching that video. Thanks so much, guys.